Okay, so first thing that we're going to do is we're going to look at the parent function. So we're going to look at the parent function of all quadratics. And the parent function of quadratic, which is it's like the root of everything. It's the base of everything, quadratic, is y equals x squared. Okay, so that's the original graph. Everything that's quadratic is originated from this one. It's either translated, stretched, compressed, moved up, moved down.
This is the basic means?
This is the basic. This is the parent function.
So it's pretty much from what we did yesterday.
Yeah, so this is building on what we did yesterday.
Oh, okay.
Yeah. Okay, so we call this parent function of quadratic, obviously. Each type of functions have its own parent function. So quadratic has its own parent function, which is y equals x squared. Okay? So if I give you the x values, which is -4, -3, -2, -1, 0, 1, 2, 3, and 4, I want you to find the y values. What do you have to do?
Replace.
Replace x with its values. So the first one, I have -4 squared. What does that give me?
16x squared.
It would be just 16. Okay? Because -4 squared, right? -4 to the power of 2, that's positive 16. And then -3 squared, that's going to be 9. -2 squared, 4. -1 squared, 1. 0 squared, 0. 1 squared, 1. 2 squared is 4. 3 squared is 9. And 4 squared is 16. Okay? So now I have the table of value. They're asking me to find the first and the second difference if needed. Okay? We know we're going to need the second difference because it's a degree 2, it's quadratic, so we do need it. But let's first find the first difference. 9 take away 16. -7. Right? Because I'm doing the subtraction. 4 take away 9.
-5.
1 take away 4. 0 take away 1.
-1.
And 1 take away 0. 4 take away 1. 9 take away 4.
5.
And then 16 take away 9. So we see that our first difference is not constant, so we have to move to the second difference. So you have to be careful here. There's some negatives, so you have to be careful. -5 take away -7. 2.
-2.
Positive.
Sorry, positive.
Yeah. Now, -3 take away -5.
2.
2. -1 take away -3.
2.
1 take away -1. 3 take away 1. 5 take away 3, 2. 7 take away 5, 2. Okay? So we notice that our second difference is constant. We knew that. We knew that because it's a quadratic, right?
Yeah.
But at least now we know for sure that we've done it correct. Yeah. Now, we're going to graph our points, the x and the y values. Okay? So if I'm looking at this graph, I have x values between -4 and 4. So I'm going to have negative and positive x values. Looking at my y values, they're all positive, okay? So I have to make sure that I have more space in the positive y. So what I'm going to do here is I'm going to graph my y-axis in the middle. My x-axis is right here. I might not be able to fit all the points because in this case I want to go up by 1 because I want to show you something very important. Okay? So that's why I'm going to go up by 1 on the y-axis. Even though we're not going to be able to fit all the points, that's okay. That's a 3. So my first point was negative 416. I can't replace that, so I'm going to move to the negative 3, 9. Okay? So I'm going to go negative 3, 9. So negative 3 and 9, so that's my point. What's my second point?
Negative 3, no, sorry.
Negative 2,
4.
4. And then negative 1,
1,
1,
0,
0, 0, 1, 1,
2, 4,
2, 4,
3, 9.
3, 9, and then I can't fit the other one. Having like 5 points on the graph is very good, right? So look how clear this is, right? It is clear that I am going to graph a quadratic function that is a smooth graph and that is open up. So if you're looking at this graph, which is the parent quadratic function, the vertex is
0.
0, 0. So remember, a vertex is a point, so it has to be x and y value. My vertex is right here, and it's at the origin, and it's 0, 0. I already said the word, okay? So it's known as the origin, right? We call that 0, 0 point the origin. Origin, yeah. The optimal value is
0, 0, 2.
it's y equals to 0. Remember, when I'm looking at the optimal value, I am looking at the y value of my vertex, right? So it's y equal to 0, and it's a max or a min? It's a min, because which way does the graph open? The graph opens up.
So, in this we need to write all this. The optimal value is y equals 0, and it's
No.
because of that.
No, you just have to say, when I ask for the optimal value, you just write y equals 0, and you say, that's it. That's all what you have to do. Okay? What's the axis of symmetry?
So y-axis. Y-axis.
It's the y-axis, yeah. So if I'm looking at the axis of symmetry, it's this one, right? And it's at x equals 0. 0. Remember, it's the x value of the vertex. So once you find the vertex, you already found your optimal value and your axis of symmetry. So the axis of symmetry is x equals 0, and we call that the y-axis. So the graph is symmetrical about the y-axis. Now it doesn't always happen that way, right? Later when I look at my transformation, I will see that it's not always the y-axis that's my axis of symmetry. How many zeros do you see here? How many x-intercepts do you see? 1. Which is?
0.
0, 0. So there's only one x-intercept. Now, here's the trick when it comes to graphing. So there is a pattern when we're graphing quadratic, okay? Other than finding points and then table of value and graphing the points, there is a pattern. And the pattern, let's see. So if I look at the graph, I'm just gonna, so if I look at the graph, I'm gonna start with my vertex. have to do, how many units do I have to go up, how many units do I have to go to the right in order to get to the first point. So I had to go up 1, over 1, right? To get to my next point. Right? Okay. How about the next one? How much do I have to go up? 5. 1, 2, 3, and over 1. Right? So for the first one, I had to go up 1, over 1. And for the second one, I had to go up 3, over 1. And then for the next point, I have to go 1, 2, 3, 4, 5, over 1. So, and then I can go over to the other side as well. So up 1 over to the other side, up 3 over to the other side, up 5 over to the other side. Okay? So this way, I start from the vertex because that's the middle of my graph, and I go up 1 over 1 to both sides, up 3 over 1 to both sides, up 5 over 1 to both sides. Now, this pattern is true for all quadratics or a multiple of it. So that means my pattern for quadratic is 1, 3, 5. Starting from the vertex, so I start from the vertex. To find my next point, I'm going to go up 1, over 1, up 3, over 1, up 5, over 1. But it depends on what kind of stretch do I have or what kind of compression. It could be a multiple of it. So that's why we say that the pattern of vertex is A, and I'll tell you why A times 1, 3, 5. Okay? If I don't have any vertical stretch, we'll talk about that in a bit, then it will just be 1, 3, 5. Okay? If I have a vertical stretch, it will be a multiple of it. So if the vertical stretch is 2, then it will be 2 times 1, 3, 5. So 2 times 1 is 2, 2 times 3 is 6, 2 times 5 is 10. So I'm going to have to go up 2 over 1, up 6 over 1, up 10 over 1. Okay? We'll talk about that in a second.
So it should be in the positive, right? Not in the negative.
For the next point, like up 1 over 1, you can go up 1 over 1 to the other side as well. So because it's symmetry, right? So I start from the vertex, right? I go up 1 over 1 to the right, and I find my point. And I go up 1 and over 1 to the left to find my next point because it's a symmetry, right? Then from this point, I go up 3 over 1, right? From that point, I have to go up 3 over 1 as well. Okay? So this is what this says. Okay? So the graph of the basic parabola without creating a table of values start at the vertex. They go right first and then up. I like to go up first and then right. So go up 1 to the right 1, up 3 to the right 1, up 5 to the right 1. And these points are located on the right side of the y-axis. Now to find the point on the left side, use the symmetry or repeat the pattern going to the left. Okay, so up 1 to the left 1, up 3 to the left 1, up 5 to the left 1. So remember the step pattern on your graph. So if I give you an equation, right, and I say graph it, whatever the equation is, right? If I say this is your equation, graph it, you're going to start from your vertex. We're going to learn all of this. You're going to start from your vertex, and then you can use your step pattern to graph your next point. You don't even have to do a lot of work to find a table of value. Okay? You can use your step pattern. So now, what we're going to do, we're going to use the parent function, and then we're going to compare the other functions to it. Okay? The other quadratic functions to it. So, because we don't see y equals x squared only, we see y equals 2x squared, we see y equals 5x squared plus 5, we see like many different things. So, no! She's mine.
I know, I'm
Yeah, just, she's gonna be, we're gonna split another Mandarin, the JKSK. Yeah, so Mandarin 1 and Mandarin 2, we're gonna split them, and then she's gonna be the lead starting. Okay, so now do you need her this week? So then she's gonna be Mandarin 7. No, Mandarin 8. We'll figure it out, I'll give you a list. Okay. All right, you're welcome. See you tomorrow. Sorry.
So this is, so now here in AX, wait,
Yeah.
AX is like to measure vertical stretch.
We're gonna talk about that. Yes, yeah, we're gonna talk about that. Yeah. Okay, so as I said, that y equals x squared is not the function that I'm gonna see all the time. Okay, so we're gonna start looking at different transformations. Okay, the first transformation we're gonna look at is when I have something multiplied by the x squared. Okay, so if I'm given a function that's y equals 2x squared, y equals half x squared, y equals negative 2x squared, y equals negative half x squared, y equals whatever x squared, just give me any number multiplied by x squared. What is going to happen to my graph? Okay? And then we're going to look at how do I identify. Okay? So what I'm going to do is I'm going to open Desmos, and we're going to graph this, and then we're going to compare, and then we will fill this out too. Okay? So at first, so always be compared to the y equals x squared. Okay, so that's why I'm going to keep y equals x squared on my function. Can you guys see this? Okay, so that's my original function, y equals x squared. Now, I'm going to graph y equals 2x squared, and let's see how is my graph going to be changed. So y equals 2x squared is my blue graph. Can you describe the difference between the red graph, which is my original graph, and y equals 2x squared? It's skinnier.
It's
Right?
the same point.
It's skinnier.
Which one's the original one?
Original one is the red one,
Yeah.
and the blue one is y equals 2x squared. So you see that the blue one is skinnier, right? Okay. Now, this is not the terminology we're going to be using. We're just looking at it. How about your vertex? Did your vertex change?
No, the same.
No. The vertex stays 0, 0, right? Did my axis of symmetry, optimal value, shape of like the way it's opening,
Yeah.
still the same. Good. Now let's look at y equals 0.5 x squared. Compare the green one to the red one. It's white. The green one is white. Why do you think that is?
Stretch. So the number 8.
Mm-hmm.
So big. Smaller.
Yeah.
The more the graph will be wider.
So
Okay.
we have the coefficient less, fewer,
Yeah, you know.
the less coefficient, we're gonna have white graph.
Uh-huh.
the point will be 1.0.5.
Yep.
So it will be more down.
Like lower. Yep. Now, let's look at y. Okay, so, or let's look at the actual terminology. All right, so we have figured out that if a value is 2 or anything that's greater than 1, right, it's gonna look skinnier, right? So I can test this. Give me any value of a that's greater than 1. 3, 7, whatever. Okay, let's try it. So if I have y equals 3x squared, look, the purple one, skinnier than the red, right? Even skinnier than the blue. If I have y equals 7x squared, right? Even skinnier, right? So if the a value is greater than 1, I am going to have a skinnier graph, okay? The bigger the a value, the skinnier it is. Yes?
Can they actually go on the actual line? Like if you go high enough, would it actually go on that line?
If you zoom it, it won't be, right? Yes, but it would look like it is, but if you zoom it, it won't be, right? Now, if I'm taking this elastic band, okay, and I want to make it wider, sorry, not wider, skinnier, what do I have to do? Which way? Stretch it up, right? If I stretch it up, then I'm going to make it skinnier, right? So you just told me I have to stretch it up to make it skinnier. So the actual terminology that we use for skinnier is a vertical stretch. Vertical means up, means like vertically, right? Up, down. So vertical, and I'm going to have to stretch it. Okay? Now, so that means if my a value is greater than 1, we're going to use the terminology, it's vertically stretched by a factor of, for this course specifically, you don't have to use the by a factor, but if you'd like to know, we use the word, so vertically stretch by a factor of 2, 3, 7, whatever it is. Okay? So vertically stretched. Okay? We're gonna write all of them. Now, if you want to make something wider or flatter, what do you have to do? You can do horizontal stretch, but that won't be, that we're not touching horizontal now. What do we do? What else can you do?
Take one,
Press it, compress it. There we go. Right? So if you want to make a dough flat, or if you want to make this flat, you're going to have to actually press on it, right? So this is what we're doing. If we have my elastic, to make it flat, I'm going to have to vertically compress it, or not flat, wider. We're going to have to vertically compress it, okay? Press on it, compress it. And that's what the 0.5, or anything that's between 0 and 1, right? 0.5, 0.75, 0.25, 0.3333, anything that's between 0 and 1, it's going to make your graph wider, and it's going to make it wider by vertically compressing it, okay? So pick any value that's between 0 and 1.
0.75.
Okay, so 0.75 x squared, right? You see it's, that's gonna look the same. Okay, this is 0.5, 0.75, where is this? Okay, let's pick 0.25.
Okay, because I'm going close to 1, that's why it's make it lower.
Yes,
thinner.
it's make it,
one.
yeah.
So I
But
need to
remember,
choose
this is your original one.
Yeah.
Okay, the y equals x squared, this one is the original one. See, it's getting even wider and wider, right? Y equals 0.1 x squared, right? It's going wider and wider, okay? So, the vertex, did that change?
no, the same.
Vertex still the same for all of them, right? The axis symmetry, optimal value, direction of opening, still the same, right? It's still opening. Good. So, vertical stretch. Yes.
What if you were to do a D? Would it go up and down?
Yes, it will. Okay? That's our next step. So yes, let's look at that. So if I have negative 0.5 x squared, okay? So that's y equals x squared. If I have negative 0.5 x squared. Look at this, okay? That negative a value, not only that's going to cause a vertical stretch and a vertical compression, it's going to cause a reflection in the x-axis, okay? So it's called a reflection in the x-axis. So if your a value is negative, your graph is going to open down, okay? The vertex doesn't change. Now, I still have a compression, right? I still have a vertical compression, but I also have a reflection. I have two things happening. And if I have y equals negative 2x squared, right? I have a vertical stretch and a reflection.
So let's say between 0 or negative 1.
Yes?
It would be the same thing as for the positive.
Yes, but you're going to add to it a reflection. So, let's write all of this down. Are we okay with this? Did we understand what's going on here? All right. So, remember that the a value is multiplied by the x squared. Okay, so what's the a value for this one? Y equals 2x squared. It's 2. And then when we graph this, what was the direction of opening? Up. Vertex? 0, 0. My vertex did not change. And then the axis of symmetry? Now, compared to the y equals x squared, what did we say happened to the it was a vertical stretch. So it was skinnier, but we're not gonna write skinnier because that's not a proper terminology, right? We're gonna say it's a vertical stretch. So you're gonna see me writing vertical stretch as BS, okay? I won't be writing vertical stretch. You can also write it for me on the test as a BS, but as long as, like, you know your terminology too, right? So vertical stretch. Okay? What's the value of A in the next one? 0.5. Direction of opening. And the vertex. Axis of symmetry is still the same. And what do we call this? Vertical compression. Right? And vertical compression is going to be VC. What's my A value for the next one? Negative 2. Direction of opening? Down. Vertex? Vertex still 0, 0. Axis of symmetry still at x equals 0. What do I have? So we have a vertical stretch, and what else? Reflection. So we have to state both of them when we're stating transformation. Okay? So it's a vertical stretch and also a reflection.
So I would write BSR.
No, you do vertical stretch, reflection by itself. They're two separate transformations.
So always if you have it as a down, so I have to write both of them, right?
Yes.
So it's reflection.
You have to write a reflection. We usually write it as, you'll see me writing it properly. So we write reflection in the x-axis, and we say vertical stretch by a factor of 2. Okay, this one is going to be negative 0.5 as the A value. Again, because A is negative, it's going to open down. And 0, 0. And that's going to be a vertical compression. And a reflection. Okay. Now, how does the value of A affect the basic parabola? Okay, so this is where we're going to write what we learned. So, the sign of A indicates the direction of opening. Of the parabola. When A is positive, the parabola opens up and has a minimum or a max. When A is negative, the parabola opens down and has a max, and this is known as a reflection. I'm going to add to it in the x-axis, because there's different types of reflections. We only learned the reflection in the x-axis in this course, but there's 2 different types of reflection. Okay, but in this course we only do reflection in the x-axis. Now, the value of A, so if I'm looking at the value of it, is it 2, is it 0.5, is it 0.3, what is it? So the value of A describes the shape of the parabola when A is between 0 and 1, the parabola is, we're going to say, wider than y equals x squared, and we know that as a vertical stretch. Sorry, that's wider, between 0 and 1. Oops, vertical compression. Apologize. And when A is greater than 1, the parabola is skinnier or narrower. Let's use the word narrower. Then y equals x squared, and we call that vertical stretch. And that A value is the one that's going to affect your step pattern. Eyes on me for a second. Remember I told you the step pattern is 1, 3, 5 multiplied by the A value, right? So when you are looking at your vertex, which is 0, 0, right? And then your step pattern, if it's, let's say, y equals 2x squared, right? Your step pattern is going to be, step pattern are going to be 2 times 1, 3, 5, because your A value is 2. Okay? So your step pattern are going to be 2, 6, 10. Okay? So whenever you're graphing, you're going to start at your vertex, you're going to go up 2 over 1. Up 6 over 1. Okay? So remember that the step pattern is multiplied by the A value. Okay? And that's what causes the stretch and the compression. Okay? Because now you're, instead of going up 1 over 1, you're actually going up 2 over 1. each graph, it's asking you to state the zeros, y-intercept, vertex, axis of symmetry, optimal value. So, I'm going to do the first one with you, and then I'll leave you guys to do the second one. Okay? I know they're not very clear, but we're going to try to use whole numbers as much as possible. So what would be my zeros for this one?
Five, zero.
So,
Minus
I think
one,
it's
minus one.
What is
negative 1.
Also,
Yeah, negative 1, and it looks like
5.
5. Okay? So we can write it in two different ways. You can pick whatever way you want. You can write x equals negative 1 and 5. Or don't write both of them. Okay, pick one. Or you can write negative 1, 0 and 5, 0. Whatever you're more comfortable with, you get to pick which method do you want. Do you want to write this x equals this or as the 2 points? What would be your y-intercept? Where's your y-intercept? So this is your graph. What is it intersecting the y-axis?
Negative two.
So y equals negative 2. So it's this one, right? That's your y-intercept. And, or how can I write it as a point?
Let's see.
Where's my vertex? Sorry?
If I put either or, I'm not gonna like lose my.
No. But pick one. Why do you want to write it? Okay. Where's my vertex?
Negative four.
2, -4. Remember, x first, y, right? So my vertex is at 2, -4. So a vertex, there's only one way to write it. What's your axis of symmetry? X equals 2. Remember that I'm looking for the whole thing. I'm looking for x equals 2. There's no shortcuts to this. Okay? It's an equation. How about your optimal value?
Minus negative four.
Y equals -4. And is it a max or is it a min? I am looking for this. When I do it with you here, that's what I'm looking for on the evaluations.
If I put optimal value like 2 -4.
The vertex is 2 and -4, right? But the axis of symmetry, it's only the x value.
So
Optimal.
Optimal is y equals -4. When they're asking for the optimal, they're asking you for the y value of. Okay.
So I just wanted to make sure, how did you get the zeros?
So the zeros is when the graph intersects the x-axis. So my graph intersects the x-axis at these 2 points.
Oh, okay, that makes sense.
Okay? So I'm going to give you time to work on this. Just use this as a 2. I know it might